Good afternoon. Welcome to the week 8 welcome to problem solving session for the week 8. So we are here to discuss the previous year questions related to week 8 lecture, and also we will see if anyone have any doubt. We will try to solve that. So let's start. First I'll start with the basic introduction, basics about the lecture part. What was taught? I will give you all a brief recap of that. So let me share my screen. So um, welcome to the week 8 problem solving session for the subject environmental chemistry. It is taught by the Professor Bhanu Prakash from Department of Civil Engineering, IIT Roorkee. I am one of the TA for this course. My name is Asma Parveen and I am a PhD scholar in Civil Engineering Department at IIT Kanpur. So we will see the first lecture, that was lecture number 36. So this lecture was about aqueous complexes and its application in reduction of the toxicity. So if there is any system, and suppose we have some heavy metals and we want to reduce its toxicity, and if the heavy metal is more toxic in its cationic form or in its free metal form, then we can add some ligands through which these heavy metal free cations can form complexes with the ligands, and eventually the toxicity of that heavy metal will reduce in the system. So aqueous complexes are important for this. There are also other applications of aqueous complexes we will see in the subsequent lectures. Also, the form of the complex, or we can say the form of the metal or heavy metal in the system, will depend very much on what is the pH of the system. At acidic pH, the concentration of different complexes will be different. At neutral pH, it will be different, and at basic pH, it will be somewhat different. So let's see the basics. So we have Bronsted acid, which are the H plus donors. Bronsted acid donates H plus, and Lewis acid are those which can accept the electrons. So here we can see that Fe3 plus has accepted one electron, and it is converted to FeOH 2 plus. The charge is 2 plus. So here there is a acceptance of electrons. So it is a Lewis acid. Generally, metals are poor in electron because they have already donated their electrons. So they can take the electrons from the ligand and they can form complexes, like they can form aqueous complexes. Next, so these are some of the terminology, like what is a complex, what is the central atom, and what is the ligand. So central atom is the atom which will have poor electron compound in the complex. It will have deficiency of electrons, and the ligands are electron rich compounds, so there is a sharing between the central atom and ligand. And next is coordination number. It is the number of ligands per central atom. So if there will be two ligands, we can see here LL is for the ligands and M is the central metal. So this is our linear complex. And if we will have four ligands, then there two shapes are possible. One is the tetrahedral, in which these three at the bottom and one ligand will be at the top. And all these distance is similar between L and M. Next, these four ligands can be all be in the same plane, and we can same plane, and we can get a square planar. Next is when we have six ligands, it will form a octahedral complex. So next is monodentate, multidentate, or chelate. So monodentate are in which there is one binding site or there is one ligand per structure. Next is multidentate. It will have more than one ligand. So next is chelate. It has multi-dentate complex. It will have more than two ligands. So next we will see the importance of these complexes. So as I said in the beginning, that the concentration of a particular species of that metal will depend very much on the what is the pH of the system. So sorry. So we can see that the total concentration of metal is not equal to the concentration of the free metal, because Fe total will be summation of concentration of all the complexes of that compound. Suppose we have taken Fe, then total Fe will be summation of Fe3 plus and other complexes which Fe will form in the system. So let's move to the next lecture. So we have continuation of the previous lecture. It is for solubility, rate constant and strength of ligands. So what is the importance for suppose we get, if we want to reduce the toxicity of some metal, and if suppose the free form of that cationic form of that metal is toxic, then we can make complexes and reduce the toxicity. Next is solubility. What happened that if the solution becomes super saturated with respect to some compound, then it can precipitate out of the system. Next is sorbability, that is sorption. If it will be favorable, then there will be sorption taking place in the system. Next is kinetics and equilibrium. Let's see, we will see this in the further section. Next, this is very important, like if we have a table, um, I think I should share the table with you all, so just give me a minute. So this is the table in which the metal, central metal is given, and I is the number of stable complexes which this metal can form, along with the values, that is log k star, log beta and log beta star. So in the lecture we have seen that K, that is the equilibrium constant, in terms of K is denoted when the ligand is in the deprotonated form. Suppose we have the H2O ligand, so its deprotonated form will be OH minus. So when the equation reaction is in the form of Al3 plus OH minus give us AlOH 2 plus, then K series is used, and each species, suppose we have to write for AlOH whole twice, then we will not write from Al3 plus, then we will write from the previous complex which was formed, that is AlOH 2 plus OH minus, it will give us AlOH whole twice. Next we will write for AlOH whole thrice, and next for AlOH whole 4 minus. This is in the equilibrium constant in terms of K. Next, when the equilibrium constant will be in the terms of K star, then we will take the protonated ligand. That is, in the previous we have taken OH minus, here we have taken H2O. So when the ligand will be in the terms of protonated and the final equation will have H plus, then we will denote the equilibrium constant in terms of K star. Next we have direct. When we write the direct deprotonated ligand, like we are writing, suppose we are writing for aluminium, then we will write for first complex for like Al3 plus OH minus give us AlOH 2 plus. Next, for if you want to write for AlOH whole twice, then we will directly write from Al3 plus. So if it is Al3 plus 2 OH minus, then our equilibrium constant we can take from the beta I. Next is beta star. So it will be for the writing the equilibrium, reaction from the initial uh, 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 cationic form of the metal, that is Al3 plus H2. This will give this, and for the next complex we will write from Al3 plus only. So this was for the this is very important. Suppose we have been given a table like this, and we have to select the values. So we know that log k It will be for deprotonated form. Next is K star. It will be for the protonated form, and next is log beta, and next is log beta star. So let's see. So K is for the deprotonated ligand, and K star is for the protonated ligand, and next beta was for the direct deprotonated ligand, in which we write the reaction directly from the cationic form of the metal. And next is beta star, in which we write the for any complex we write from Al3 plus only. So let's move to the next part. So this is for strength of the complexes. Multidentate will be having more strength than the monodentate. If there will be more charge, then it will be more stronger. And this is the ligand preference for some of the metals. So here example was shown to write the all the complexes of aluminium in the hydroxide system, that it is a system has water and only aluminium is added. So it was shown here. It is shown here. First we will identify the species, then we will identify the components, we will write the formation equations, then we will write what is the total concentration of all the components in the system, and like this we will get the total concentration of the components in the system. And next we can, if we have given some values for aluminium and Hd, then we can directly put it in the visualminteq and find do the further calculations. Lecture number 38. So this was about aqueous complexes of aluminium. Here an example was shown by solving the problem based on aluminium. So here from the previous lecture, these are taken. And that is H total. This was the equation for H total, and this is the equation for Al total. And we know that we can write these complexes in terms of beta star. So we know that beta star is for the uh, for writing directly the equation for complexes from the cationic form of the metal, and the ligand will be in the form of protonated form, that is H2O, because ligand here is OH minus. So here it is written for AlOH whole twice, AlOH 2 plus, and similarly it is written for all the four complexes of the aluminium. So we can see that we can replace the concentration of all these species in the terms of Al3 plus and H plus. So finally we will get this equation in the form of H plus and Al3 plus. And similarly we can also replace these complexes concentration of these species using Al3 plus and H plus. So we have two equations and we have two unknowns, that is Al3 plus and H plus. By solving these two, we will get the H plus and Al3 plus. So after we have got the pH, that is H plus and Al3 plus, we can subsequently put these in these equations, and we can find out the concentration of the different complexes of the aluminium form. So here our example is shown that suppose we have added 10 raised to the minus 3 molars of AlCl3, and we have added this much of NOH. So total HT will be minus of this, and total Al total will be AlCl3, that is 10 raised to minus 3m. And similarly we can put the value of total Al3. We can solve this equation of course we cannot solve it by calculator, but we can solve this by in Excel, and we will get the value of H plus and Al3 plus, and we can finally find out the concentration of all the complexes formed. Or directly we can do this in the directly we will see how to solve this question in the visualminteq. We just have to put all concentration of total concentration of the components, and visualminteq will do the calculation. It will show the give us the total or sorry concentration of each of the complexes formed. Next, suppose that till now we have seen the hydroxide complex. Suppose we are adding fluoride also in the system. So aluminium will combine with fluorine also, fluoride ion, and it will have other fluoride species of the aluminium also. So if we have solved for OH minus, similarly we will solve for AlF, and Then we will find total H plus, total Al3, sorry, total aluminium and total fluoride ion, and we can do the calculations. Next, move to lecture number 4th. It is about aqueous complexes of mercury. So here example was given in which the more important complexes and also the components which we have to take in visualminteq was already defined in the question, and also there was one assumption that S2 minus as a species is uh, that it is so large that it will not present at reasonable concentration at most pH, so we have to ignore this. So here example was here the solution was given based on these assumptions. What we have taken the HgOH whole twice and HS minus as the components, and obviously H plus will be the component, and all the formation equations have been shown. The total concentration of components has been calculated, and we can finally solve to get the uh, concentration of each complex or whatever is asked in the question. Next is about plotting log C pH diagram. So we will also see an example in our questions which we will solve, where we will learn how to solve a log C pH diagram using visualminteq. So here the log C pH plot is plotted. I think the plot must be here. So this is the log C pH plot for the given system. So let's move to the last part of the week 8 material. So it is about precipitation and dissolution. So it is introduction about precipitation and dissolution was given. So these are some of the applications. Like if we want to remove the toxic metals, then we can add some compound or chemical in the system which will precipitate out the heavy metals complex, which will complex with the heavy metals and precipitate out of the system. Next is for everyone knows that for hardness removal we add lime or lime, or for removal of temporary hardness we boil this water, and then the calcium and magnesium which causes hardness. Generally hardness is caused by multivalent ions. So these calcium magnesium reacts and they form precipitates and comes out of the water, and the hardness is removed. Next is phosphorus removal. In wastewater, in surface water or in oceans, there is lot of problem of eutrophication, and eutrophication is caused by excess nutrient discharge in the water bodies by human activities or by naturally. So generally phosphorus is the limiting nutrient which limits the eutrophication. So if there is a surplus amount of phosphorus in the system, then eventually there will be lot of growth of algae, and it will lead to eutrophication. So for removal of phosphorus also, some generally aluminium and iron metals are added in wastewater treatment plants to precipitate it out as aluminium phosphate or iron phosphate. Also after the formation of the aluminium and iron flux, these precipitates out of the system, and the water is free from phosphate. Next is iron or manganese removal. We can also precipitate out iron and manganese in the form of ferric oxide and ferric hydroxide and manganese oxide, and water will be free from all these. Also nowadays there is lot of work going on recovery of nutrients from the wastewater, in which we precipitate out the nutrients from the wastewater in some useful form which we can use in industries or agriculture. And also there is lot of research going on recovery of in fact heavy metals out of the sludge, because all the heavy metals and nutrients are taken by the it will depend what process we are operating to treat the water. Depending upon that, the overall concentration of heavy metals and phosphate will depend upon the will be vary in the sludge, and from the sludge recovery of heavy metals and nutrients is being done. Next is kinetics. Kinetics is also something which plays role in the formation of something. Suppose if the kinetics is very fast, then the system can reach equilibrium in some time. But if the kinetics is very slow, then it can take days to months to for the system to equilibrium, go to equilibrium, and it will look like in some system that where the kinetics is so much slow that it takes years to reach the equilibrium. So we take that system as irreversible system. But no system in general is irreversible because every system is reversible. Next, here the example of coagulation was given. So I think these were for the week 8 lecture materials. So here we have seen the sir has taught about precipitation in the form of Fe2 plus and Fe3. Example was given in which it was shown that 100% 85% Fe2 plus is in the system, I guess, or something like that, and there was precipitation was 100% precipitation in the form of Fe3 plus. So depending upon this, we can choose which of these out of these two, which metal ion we have to choose to precipitate out. So let's move to the question. So let's go here. Sorry. So the first question is, so five statements are given and we have to choose the statement which out of these five statements there can be one statement true or there can be more than one statement which are true. So the first statement is complexation generally increases the total concentration of metal ions in solution. Second is the extent to which Ca2 plus, that is calcium ion, can be removed by lime softening to form calcium carbonate may be limited in part by soluble complexes of calcium. C is complexation decreases the toxicity of metal ions whose predominant toxic species is the free metal ion. Fourth option is in COD test, mercury salt is added, otherwise the COD obtained will be underestimated. And last is during hardness test, we add EDTA which allows magnesium metal ions to be free so as to give true endpoint of titration. So out of these five options, we have to select which of these options are true. So let's see. Let's start with the first one. So the first option is complexation generally increases the total concentration of metal ions in the solution. So this statement is true because through complexation, the metal ion will not, as we know, the complex are soluble in nature. So through complexation, the total concentration of metal ions in the solution will increase. But if this statement was like that, complexation generally increases the concentration of free metal ion in the solution, then that would be wrong. But since it is total metal concentration, that is summation of all the metal complexes in the system, so this is true. Next is the extent to which calcium can be removed by lime softening to form calcium carbonate may be limited in parts by soluble complexes of calcium. So this is also true because we know that. So I think I should share my other screen. So just give me a minute. So we were discussing about the option number B, sorry, that the extent to which calcium can be removed by lime softening to form calcium carbonate may be limited in part by soluble complexes of calcium. So it is true. Let's see what happens. That calcium plus carbonate will give us CaCO3, and the K, that is equilibrium constant for this, will be activity of Ca2 plus. Okay, I think it should be in the reversible manner. So we can write the activity K1 by activity of C. So let's see here that CaCO3 will dissociate into Ca2 plus and carbonate. So if Ca2 plus can form complexes with some complexes with hydroxide or other ligands in the system, then concentration of Ca2 plus will decrease. And since the Ca2 plus concentration will decrease, then finally the concentration of CaCO3 solid will decrease. And softening will be influenced by the concentration of the Ca2 plus in the system. So A is correct, B is correct. So let's see the third option. Complexation decreases the toxicity of metal ion whose predominant toxic species is the free metal ion. So I think this is also correct, because due to formation of complexes, the free metal ion concentration will decrease, and eventually if the free metal ion is the toxic one, then its concentration will decrease, and eventually the toxicity will also decrease. Option number D is, in COD test, mercury salt is added, otherwise the COD obtained will be underestimated. So this is false, because mercury is added to oxidize chloride, and if will not be added, then K2Cr2O7 and the H2SO4, which is added in the COD test, that will be consumed to oxidize chloride, and eventually the COD will be overestimated. So this is wrong. Next option is, during hardness testing, we add EDTA, which allows magnesium metal ions to be free so as to give true endpoint of titration. This is also wrong, because first the magnesium we add EBT through which magnesium and EBT make complexes, and finally it is titrated with EDTA, which forms the complex with magnesium. And in what happens in the complex of magnesium and EBT, that EDTA replaces the EBT and magnesium EDTA complex is formed, which give us the endpoint with change in color to blue. So the option A, B and C are correct. So let's move to the next question. So here these are the explanation. So we have to solve this in visualminteq. That use visualminteq to determine the dominant species of cadmium in seawater. Assume that total cadmium is 4 microgram per liter and the ionic strength is 0.7 molar, and consider these species as possible complexing ligand. Okay. Use the concentration of these ligands given in the table below. The dominant dissolved cadmium species is, so 4 options are given, out of which we have to find out which is the dominant dissolved cadmium species. So in the table, the concentration of sulfate is given, chloride is given, alkalinity and pH are given for the system, along with the concentration of total cadmium and ionic strength. So what we are going to do, we will feed all these values in the visualminteq and see out of all 4 which is the dominant one. So let's go to visualminteq. So let's see what was the question. Question is that total cadmium is 4 micrograms per liter. So let's go to visualminteq. I am open. Let's first reset this. So first let's add cadmium, that was micrograms per liter. So we have micrograms per liter. We will add cadmium, that is Cd plus 2. Cadmium is 4 micrograms per liter. So we will add 4. We will add to the list. Next we have been given sulfate. Okay, let's add this. So sulfate is 2710 milligrams per liter. So let's change the unit to milligrams. It is 2710 milligrams per liter. Next we have chloride ion. Chloride is 19400 milligrams per liter. Also pH is fixed at 7.9. Ionic strength is fixed at I think 0.7. Yes, 0.7. And also alkalinity is given, so we'll add alkalinity. It is 120 milligrams per liter as CaCO3. So it is 120. So let's first check the list which we have added. So this is correct. All these are in milligrams per liter. So we'll go back and we will run the minteq. So as we can see, we have fixed the pH at 7.9. Ionic strength was fixed. So this is the overall distribution of the species. So we will go to view species distribution. So from here we can see the distribution for carbonate, for cadmium, sulfate and chloride. We can see that sulfate and chloride are 100% at the given pH. And we have to see the cadmium species. So we can see that CdCl2 aqueous is 49.448%, and this is the highest percentage of the cadmium species. So CdCl2 is the dominant one, and next to CdCl2, CdCl plus is the dominant species. So the option answer is this one, CdCl2 aqueous, because it is 49.448%. So let's go to the slides. So CdCl2 aqueous, that is option CdCl2 aqueous, that is option C is correct. So let's move to the next question. So these are the slides which we have added. So again it is a numerical. The question is, the owner of an industry that generates wastewater containing both silver and mercury, Ag plus and Ag2 plus, is considering two options for discharge of the water after treatment. So the first option for discharge is, one option is to discharge the water through through an ocean outfall, in which case the initial dilution is predicted to yield concentration of this much of total Hg and this much of total Ag. So we have been given the total concentration of Hg and total Ag. And the next option is to discharge to a larger river, in which the dilution would be faster and more extensive, so the total concentration of the metal near the outfall would be lower by a factor of 10 to that of yielded by ocean outfall. So whatever the concentration is at the ocean outfall for these metal, it will be lowered by a factor of 10, that it will be divided by 10 in the river outfall, because of the dilution in the extensive dilution in the river. Again, question is, both Ag plus and Ag2 plus are more toxic as free ions than as complexes. So the free ion of these metal are more toxic than the complexes. The major complexing ligand in the two potential receiving waters are chloride and sulfate, and concentration of both chloride and sulfate for ocean and river system is given. Both solutions are at pH 8 and the ionic strength is fixed in the ocean and river. The suitable discharge option you would recommend to minimize toxicity near the outfall. So we have to discharge some water after treatment from an industry. We have two options. First one is ocean outfall and second is discharge in the river. So in ocean outfall, there is concentration of mercury, total mercury and total Hg is given, and for the river, it is said that the concentration will be divided by a factor of 10. And next, it is also said that the free metal ion is more toxic, so we do not want free metal ion concentration to be high. We want it to be very less. And next, we have been given the concentration of chloride, sulfate. We have given value for pH and ionic strength in both river and ocean system. And we have to find out the most optimum one, which we can minimize, which will minimize the toxicity near the outfall. So first we will solve for the ocean outfall, and next we will see for the large river and see in which we are getting the least concentration of these two metals in the free metal ion form. So let's go to minteq. So here Ag2 plus total Ag is given as 2.5 milligrams per liter. Mercury is given as 0.04 milligrams per liter. Sulfate is 2710 for milligrams per liter, and chloride is this much. pH is 8 and ionic strength is 0.62. So all these values are for the ocean. So let's go to minteq and solve. So we'll go to back menu. We will first reset it. Now let's start putting the values. So the pH is fixed. I think it was 8. Yes. The pH is 8. Next, ionic strength is also fixed. It is 0.62. Okay. Next, we have been given silver Ag. Total silver is, I guess, 2.5. So let's change the unit to milligrams per liter. So it is 2.5 milligrams per. We will add to list. Next is mercury Hg. It is 0.04 milligrams per liter. We will add to the list. Next we have sulfate. It is 2710 milligrams per liter. 2710. Next is chloride. And it is 19400 milligrams per liter. So 19400. So let's see, we have added all the things. So we have added mercury, Hg2, sulfate, chloride. Okay. We have fixed the pH at 8 and ionic strength is 0.62. So we will run the minteq. So this is the overall species distribution. The pH is already fixed at 8 and ionic strength at 0.62. So we can see the equilibrated mass distribution. In here it is given in the terms of total dissolve. What is the percentage dissolved? What is the percentage that is sorbed? And what is the percentage that is precipitated? But we will see this in the precipitation of the solids. Here we will see the species distribution. So here we can see that almost 99.99% of chloride is in the form of Cl minus, and Ag plus is 0.9%, and other complexes we do not have to worry about that because we do not want the silver as free. Okay, here there is Ag plus is not in the free form. It has complex with chloride. Next, for mercury also we cannot see the free form of the mercury. So discharging in ocean is a good option. Let's also see for the river system. So here we can see that the Ag plus concentration is very less. It is 10 raised to minus 10. And Hg plus 2 is 10 raised to minus 21. So it's way too less. So let's see next. in the river system. So let's go to the slides. So here we will, here in the, it was given that there is lot of mixing in the river, so there is a reduction in the concentration of Ag plus and Hg2 plus by a factor of 10. So now the Ag plus concentration is 0.25 and Hg2 plus is 0.004. Also sulfate and chloride has changed, and also ionic strength has changed. Let's change all this. So now we can directly go and edit here. So Ag plus is 0.25, Hg plus is 0.04, sulfate is 12 milligrams per liter, okay, and chloride is 35 milligrams per liter. Let's go back. The pH is fixed at 8 and ionic strength has reduced to 0.01. So let's run the minteq. We have all changed all. Let's run it. So this is the overall species distribution. We can see that the Ag plus concentration here has increased from, in the ocean outfall it was I think 10 raised to minus 10, but here it is 10 raised to minus 7. And also Hg plus 2, it was 10 raised to minus 21 in the ocean, and here it is 10 raised to minus 18. So the concentration of free metal ions has increased in the river system. And now here if you see the species distribution, so here we can see that Ag plus, that is free metal ion, is 36%. And the ocean outfall, it was very less, it was less than 1%. And it was not shown here in the species distribution. We have just seen in here that Ag plus was 10 raised per something into 10 raised per minus 10. And also we can see that mercury concentration is very less, that is free mercury metal ion concentration is less, but in the river system the concentration of the free metal ion, that is Ag plus, has increased to 36%. So Ag plus is toxic in free form, so river is not the correct source for it is not correct to dispose the waste in the river system. So the question was, the suitable disposal option you would recommend to minimize toxicity near the outfall is, so it will be ocean outfall, because in the river system we have seen that the concentration of Ag plus is increasing. There is no, the concentration of mercury is very less, but Ag plus is increasing over more than 30%. So ocean outfall is the correct source where we can discharge the wastewater after treatment. The wastewater which is given here in the question after treatment. So these are the screenshot which I've added for the question. Next is, a solution is prepared by adding aluminium fluoride 0.1 molar in distilled water. If H plus, F minus and AlOH whole 3 aqueous are selected as components, then which equation given below are correct? Consider no precipitation formation. So here a system is given in which aluminium fluoride is being added in distilled water, and we have already given the components that we have to consider H plus, F minus and AlOH whole 3 as the components, and we have to find out the total, we have to find out which of these options are correct. Okay, let's see how to solve this. So we have the question here. So just first let's write down what are the species and components in this system. Actually, component is already mentioned in the question. So let's write what are the species. So we are adding AlF3, which will dissociate as Al3 plus and 3F minus. So species will be H plus, OH minus and H2O definitely. Next species will be Al3 plus, AlOH whole, 2 plus, AlOH whole 2 plus, AlOH whole 3 aqueous, AlOH whole 4 minus, and next will be, we are adding fluoride, so it will form HF. In the question it is not mentioned that aluminum is will form complexes with fluoride, and also we can see in the option that fluoride species of aluminum are not present anywhere, so we will not consider that. So next, what are the components? So components are already mentioned in the question: H plus, F minus and Al OH whole 3 aqueous. So these three are the components. Now let's start writing the formation equation. So let's write in the next slide. So first we will write for H plus. So H plus will give us H plus. Next we will write for OH minus, that H2O minus H plus will give us OH minus. Next we will write for the next species, that was Al3 plus. So we know that, but we have to write in the terms of AlOH whole thrice. So we know that Al3 plus 3H2O will give us AlOH whole thrice aqueous plus 3H plus. Yes. So we can rearrange this equation in terms of Al3 plus will be equal to uh, AlOH 3 aqueous plus 3H plus minus 3H2O will give us Al3 plus. So this is the first, this is the second, and this is the third formation equation. Let's write the fourth one. The next species was AlOH 2 plus. So we know that Al3 plus 1 H2O will give us AlOH OH 2 plus H plus. But we have to write in the terms of AlOH whole 3. So we can write like either we can write Al3 plus from this equation. Let's write from that equation. AlOH whole 3 aqueous plus 3H plus minus 3H2O. Next is plus H2O. It is giving us AlOH 2 plus H plus. So AlOH 2 plus will be equivalent to AlOH whole 3 aqueous 3H plus minus 1, that is 2H plus minus 2H2O, that is equal to AlOH 2 plus. So we can either write AlOH, we can replace Al3 from here, or we can simply use this equation. So it is better to replace the Al3 plus using this in the all the equation, all the species. So this is the fourth. Next see list. Now sorry. Let's see for the next species, that will be AlOH whole 2 plus. So we know that Al3 plus 2H2O will give us AlOH whole 2 plus 2H plus. Here also we will replace aluminium 3 plus using this equation. So let's do that. AlOH whole 3 aqueous plus 3H plus minus 3H2O plus 2H2O will give us AlOH whole 2 plus 2H plus. So let's simplify this reaction. We will get AlOH whole 3 aqueous 3H plus minus 2H plus H plus minus H2O will give us AlOH whole 2 plus. Now let's try for, I think I should use a new slide, it would be better. So next will be Al, that is aluminium AlOH whole 3 aqueous. It will be, this is the component, so we do not have to modify it. It will be given by AlOH whole 3 aqueous. Next we will write for AlOH whole 4 minus. So we know that Al3 plus 4H2O, it will give us AlOH 4 minus plus 4H plus. Now let's just replace Al3 plus from the previous equation. In the terms of AlOH whole 3, it was AlOH whole 3 aqueous plus 3H plus minus 3H2O. So here it is 4H2O AlOH whole 4 minus plus 4H plus. So the final, let's write the final reaction equation. It is AlOH whole 3 aqueous. So 3H plus, and for that will be minus H plus H2O. It will give us AlOH whole 4 minus. And the next species was HF, that is H plus F minus will give us HF. So these were the species present. We have written the formation equation for all the species. Now we will prepare the W. So let's go to the next slide. So first let me write all the formation equations here. So quickly I will write all the formation equations so that it will be easy to prepare the table from here on by seeing the reaction equation here only. One thing I have mentioned, I have written the AlOH whole 3 in not as aqueous. These two are similar, but the thing is I have represented in the form of AQ for aqueous. Okay, so these are the formation equation. Let's prepare the W. So in the horizontal row, we will write all the components. Components are given as H plus, F minus, sorry, and AlOH whole 3 aqueous. So in the vertical column, we will write all the species. Species are H plus, OH minus, Al3 plus, AlOH 2 plus, AlOH whole 2 plus, AlOH 3 aqueous, AlOH 4 minus, F minus, and HF. All these are the species. So let's see. So 1H plus will give us H plus, F minus, nothing, it will be 0, 0. For OH minus, we have seen H2O minus H plus, so minus 1H plus, 0, next 0. So for Al3 plus, we have seen for Al3 plus that there is 3H plus, so 3H plus, and 1 no F minus, so it will be 0, and 1 AlOH whole 3 give us Al3 plus, so it will be 1. So let's see for AlOH 2 plus. So this is the equation. So there is 2H plus, this is 0, and this is 1. Next is this one AlOH whole 2. So 1H plus 0F minus and 1 AlOH whole 3 aqueous. Next is AlOH whole 3 aqueous only, H plus 0, 0F minus and 1 here. Next is AlOH whole 4 minus, minus H plus from here, 0F minus and 1 this. And for F minus will be equal to F minus only because this is a component. It will be 0, 1, 0 and HF will be 1H plus and 1 F minus gives us HF and it will be 0. So all these this will give us total H plus and this will give us the total H whole 3 aqueous plus whole 3 aqueous total concentration. So let's see what is the final equation we are getting for H total and AlOH whole 3 total. H total is H plus, we will write in the terms of activity, minus OH minus plus 3Al3 plus 2 AlOH 2 plus 1 AlOH whole 2 plus. Next is it will be minus AlOH 4 minus and plus HF. So this is the overall reaction for H total. Similarly, we will write for AlOH whole 3 total. We will write for Al total. It is Al3 plus AlOH 2 plus AlOH whole 2 plus AlOH 3 aqueous plus AlOH 4 minus. So this is the final equation for total aluminium and total H total. Let's write it here only. So let's go back and see which of the options that were correct. So for H total, A is correct. And for Al total, C is correct. So A and C are the correct option for this question. So let's move to the next question. So the question is, a solution is prepared by adding aluminium fluoride 0.1 molar in distilled water. Predominant aluminium species at pH 3, 7 and 10 at equilibrium respectively are. Consider no precipitation formation. So we are adding AlF3. So AlF3 will dissociate and it will give Al3 plus and 3F minus. So total Al concentration will be 0.1 molar and total F concentration will be 3 into 0.1, that is 0.3 molar. So we have to find out the dominant species at pH 3, 7 and 10. So what we will do in visualminteq, we will put this concentration of aluminium and fluoride. We will fix the pH at 3, 7 and 10 and we will see what are the dominant species. So let's see. So here we have added H plus, Al3 plus, F minus, and after running and fixing the pH at 3 and running the minteq, we are getting at that at pH 3, AlF3 aqueous is the dominant form. So let's see for pH 7. Okay, let's go to minteq and solve this. Sorry. Let's solve the question in minteq. So we have seen the distribution at pH 3. Let's see at pH 7 and 10. So first let's reset this. So pH is fixed at 7. Okay. Let's add aluminium is 0.1 molar. Okay. And fluoride was, yes, fluoride is 0.3. Let's check the species. Okay, we have added it. Now we will run the minteq. So we have already fixed the pH. This is the anic strength which is being calculated. Let's see the species distribution. This is the overall concentration of all the species here, and along with its activity, let's see the distribution of various species. So here we can see that for fluoride, AlF3 aqueous is the dominant form, that is 66.490. So out of all the complexes of aluminium fluoride and aluminium hydroxide complexes, AlF3 aqueous is dominant at pH 7. So now let's check for pH 10. It was 10. Yes, we have to check for pH 10. So we will change the pH and fix it to 10, and again we will run the minteq. So we can go directly to species distribution, and here we can see that aluminium had AlOH4 minus, this one is the dominant, sorry, AlOH4 minus, it is 81.675. So this is the dominant species at pH 10. So let's go back and see what options we were having. So we have seen that at pH 3, AlF3 aqueous was the dominant species. AlF3 this is dominant. Next, at pH 7, AlF3 was the dominant. Okay. And at pH 10, AlOH4 minus was the dominant. So correct option is option A. So option A is the correct. Let's move to the next question. So these are the screenshots which I have added. So next question is, a solution is prepared by adding aluminium chloride 0.01 molar into distilled water. pH can be adjusted by adding NaOH or HCl into the solution, the pH at which aluminium hydroxide starts to precipitate is. So this is the first question based on precipitation. So we are adding aluminium chloride in the system and we have to see at what pH aluminium hydroxide starts to precipitate. So let's go to Minteq and solve this question. So first we will reset everything. We are adding aluminium chloride. So let's add aluminium. It was I think 0.01 molar. Next was chloride. It will be 3 times 0.03. Now we have to see the whether aluminium hydroxide is precipitating or not. So we will go here solid phases and excluded species. So here four options are given. So we will go to specify possible solid phases, in which we can specify all the possible solids which all the possible solids which have possibility of forming in the system. So let's limit those to the species, all the solids that are based, that will be formed based on the species which we have added. So let's aluminium. We have to. It is asked that at what pH aluminium hydroxide, that is AlOH whole 3, is starting to be formed. So let's add this. Next we will add, and we can also check from list of possible species. So it is being added. So we'll go back to main menu, and also let's see what is the pH here. So the pH is 3.691, and we can see here, see the saturation indices. So here we can see that dipore and gibbsite are having saturation index greater than 0. So these two are the are precipitating in the system, but we have to see for AlOH whole 3, which is undersaturated at this pH. So let's first start by adding NOH, that is base, because generally what happens as the pH increases, there is the solubility of the compound decreases, and it starts pH comes at some basic pH, it starts precipitating and forming solid in the system. So let's start with NaOH first. So let's go back. We'll go to multi problem sweep. Okay, we just have to increase the pH, so we can use sweep one parameter is valid. So we will only sweep the pH. So we will sweep the pH, and let's start with the pH value of 1. Give increment of 0.2. So let's solve for 65 number of problems. Let's add all the species which we want to see. Let's start Al3 plus concentration. Okay, we can then directly add the solid phase AlOH whole 3 and see what is happening to this. We will save and we will simply run the minteq. So we have started with pH 1. So let's see, this is the overall distribution of the aluminium and chloride species at this pH. Next we can see saturation indices from here, and next is the equilibrated mass distribution. We will show the percentage of solids forming, and here is the selected sweep results. So here we can see that the sorry, I have added the concentration. Okay, no problem. We can see from the concentration also that till pH 4.2 nothing is being formed, and also we can see that 4.4, 4.6 and 4.8 are showing red. So there is some error which has occurred during execution, but we can see that around 4.6 aluminium hydroxide has started being formed, and at 5 it is, we can see that it is 9.6 into 10 to the power minus 3 molar is the concentration of AlOH whole 3 aqueous form. So this is, we can see that it is number 21. So we can also go to here. So there was error in 19, so we can go to 21. And we can see the saturation indices. All these solids are supersaturated, and let's see. We will see the amount of finite solid. Since we have only mentioned AlOH whole 3, we will get only the amount of this solid. If we have added the other solid, then it would have also been shown. So we can see that at around pH 4.6 or 4.8, AlOH whole 3 is starting to form. So let's go back. So here the options are 3.4, so here the options are 3.4, 4.8, 6. So around 5 pH, that was between 4.6 to 5. AlOH whole 3 was forming. So the correct answer is option B. That at around pH 4.8, AlOH whole 3 solid starts to precipitate in this system. Let's move to the next question. So here a solution is prepared by adding AlCl3 into distilled water. Then out of these compounds, the dominant species at pH 3, 5 and 11 are. So we have to find out the dominant species at pH 3, 5 and 11. So we have also solved a similar question. So let's go to visualminteq. So we have added, let's fix the pH at 3, because first we have to find out at 3, 3, 5 and 10. So at 3, so let's remove all these. Sorry. So let's see the species distribution from here. We have fixed the pH at 3 and we have already added the aluminium and chloride in the previous question, and I have solved from there only. So we can see that 99.283% is Al3 plus. So at pH 3 the dominant form is Al3 plus. Next we can see for C at pH 5, I guess. So it was 3, 5 and 11. So let's go back. Let's fix the pH at 5. We will run the minteq. Some error is showing. I don't know why some error is showing. I don't know what is error 62. Let's see at pH 11 what is showing. So it was not running at pH 7, I guess. I don't know why. At pH 5, but it is running at pH 11. So let's see the way species distribution. So that is okay. AlOH whole 4 minus is the dominant species at pH 11. At pH 5 it was Al3 plus. But what I have forgotten to add in this question is that we have also checked for Al aluminium hydroxide solid, so which we have will have to be to specify from here. Let me add that. So now let's fix the pH at 7 and see if we are able to run it or not. So this was a problem because I forgot to add the solid which may precipitate in the system. So it was aluminium hydroxide. Now let's see the various species distribution. So from here we can see that, okay. So this is for the distribution of the dissolved species. So we cannot see the solid forming here, because but here we can see that aluminium hydroxide is getting precipitated. So for this question, I think we have to plot the log C pH diagram, and then we can see the dominant form of the species. Because we are not getting for aluminium hydroxide, because at pH 7, 81.11, so that is this one is the dominant aluminium species which will be present, but also solid is being formed, and there is no solid form of aluminium mentioned here. So let's plot a log C pH. So for preparing a log C pH for this question, we will have to go to multi-sweep problem, and we will sweep one parameter pH. We have added that 65 number of problems. Start value will be 1. Increment value will, let's take 2. Let's specify all the compounds or species along with its log concentration. Let's start with AlOH. Let's start with aluminium. It will be log concentration. Let's add this. Next, let's start with this one. Next, aluminium complex. So these are the hydroxide complexes of the aluminium along with the free metal aluminium ion, and last is I have added the solid phase also. So after plotting the log C pH, we can see which of the species is dominant as pH 3, 5 and 7. So what we can do is, yes, we have added the pH. We can go save and back. We can run the minteq. So here we can see it has started from pH 1. We can go to the selected sweep results. So this is the overall sweep result, which starts from pH 1 goes to pH 13.8. Okay, I will add one more step, 66, it will give us to 40. So this is the log concentration for all the species which we have added, which I have added. So we can, let's just add one. Let's do it 66. Sorry. So we can simply print it to Excel. So we have got all the values along with the pH, log concentration of all the species along with the pH. What we can do, we can simply plot a log C pH for this, and we will get the concentration. One more mistake I have done is that I have taken all the species in log, but I forget to take forming solid in the log. So let's go back. See, I have not taken it in the terms of log, so let's add in the terms of log. So here we got all the log C concentration of all the species along with its pH. We can plot a graph between log C of the species with pH. I have already plotted it. Also, we can see that in the minteq at 3 points error was showing. So we will remove those 3 points. I think it was 4.4, 6 and 8. These three were the points. So what we can do is we can remove these 3 points and we can plot the graph. Let's see, I have plotted the graph here. So here is the graph. So these we can see that at pH 3, this blue line is the dominant species. It is Al3 plus. Okay, we were also getting this from the running the minteq as at 3. And at pH around 5, we can see that this green line, that is AlOH whole 3 amorphous forming aluminium hydroxide solid, is the dominant one. And we have to see at pH 11, I guess. So at this pH, AlOH 4 minus is the dominant species. So we can either find out the dominant species by fixing the pH in minteq and finding out which is the dominant species from view species distribution, or we can simply plot the log C pH by sweeping the pH in the visual minteq and then plotting the graph. So by plotting the graph, we are also getting the essence of what is the distribution of all the other species at different pH. So we can see that this is for AlOH plus 2. We can also add H plus and OH minus, and we can get this graph. So let's go back. So we have to find out what is the dominant species at pH 3. So at pH 3, Al3 plus is the dominant species. Next, at pH 5, AlOH whole 3 solid, that is amorphous form of aluminum hydroxide, was the dominant species, and at pH 11, AlOH 4 minus was the dominant species. So I think for 7, option D is the correct option. So I think these were the questions for assignment 8 of the previous year. So I hope you all are going through the lectures and also solving the questions, doing good in your assignments, and hope you all are sitting for your end written examination for this course. If you have any doubt, then you can ask, or otherwise we can end the session here. So from the starting, we have seen the kinetics, then we move to the acid basis, and that is we are finding the pH of the solution. Then we have seen alkalinity, buffer intensity, acidity, and then in the week 8, it was about the formation of complexes. And in week 9, I think it will be about the precipitation of the solids. And after week 8, only a month is left, and there are 4 sessions now for week 9, 10, 11, and 12, and then this course will end. I hope you all are doing well. So if you I think these were the questions which were in the last year previous year assignment questions. So these are for the today. So thank you so much. Have a nice day.